Welcome to the project Analog Computing Programming Without a Language. This is a project for Harvard CS50. My name is Klaus, I'm a German living in France. Let's go with this documentation. What is to do? Implement a program that simulates an analog computer with the possibility to run different analog programs on the simulated machine. I call it a digital analog computer. In order to understand, we look first for the question, what is an analog computer? An analog computer is a special form of a computer and was mainly used to solve dynamic problems. The basic principle is first to build a model of a process, usually in mathematical form as differential equation. Such a mathematical model is then translated in a further step into a physical model, which is formed by an analog computer. Before all the following details, a more general view. In the real world, we find some phenomena. We describe it with text, a picture, a video, or something else. Often we have the question, why is this and that? What are the relations? For a good job, we use mathematics. What are the equations? What are the solutions? What are the useful parameters? A really good practice is to solve it with an analogy. Then we must not calculate. So we draw a flow diagram, choose a model, here an analog computer, and run the model. If everything is fine, we understand that the real world is a real world with differential equations. This demonstration is divided in 6 parts. Part 1, what is an analog computing? Part 2, let us compute analog, an example. Part 3, the digital analog computer. That's the main project. Part 4, testing. Is the software working fine? Part 5, an application, predators and preys. And part 6, the end and more. Part 1, what is analog computing? Two highways are merged into one. The resulting number of cars per time unit is equal to the sum of the cars of the previous highways. Mathematical model is cars 1 per time unit plus cars 2 per time unit equal all cars per time unit. Such a simple addition can be realized physically with an electric circuit of 3 resistors. Remember Kirchhoff's current law? The algebraic sum of currents in a network of conductors meeting at one point is 0. I1 plus I2 plus I3 plus and so on equal 0. The current E is positively or negatively signed according to the direction towards the node. So the electrical model for the car equation is I1 plus I2 equal I3. Now we make an analog computer out of it. With the 2 potentiometers we enter the number to be added. In the example, we set the current intensity. The measuring device on the right-hand side shows the result. Usually, a symbol notation is used. For the highway, we have the flow diagram. I plus I1 plus I2 is, that's a technical detail, minus I3, we invert the sign with a force symbol, an inverter year signed as in summer. So we have I3. The language of programming are the symbols. Classical analog computers have a set of different operation units, like shown in this short table. There is one thing to pay special attention to: the integrator. An analog computer can integrate by nature, by its construction. That's a very special quality. Let's look for it. The integrator. Let us take a bucket into which water flows from a water crane. We can set how much water per minute flows into the bucket. This is the change of the amount of water in the bucket. The bucket stores the water. If 1 liter per minute flows into the bucket, after 3 minutes there are 3 liters of water in the bucket. Mathematically speaking, the water in the bucket is the sum of the water that flows into the bucket. Or to put it sloppily, the bucket is the integral of the water crane. This can be done electrical. If a capacitor is charged with a constant current, the flowing water, the amount of charge in the capacitor, water in the bucket, is mathematically the integral over the input current. And it's only one more step, and we have an analog computer. An analog computer provides physical, mostly electrical systems that the user cleverly connects to each other. The computer does the calculation on its own, only models are selected. Therefore, it is a form of declarative programming. An analog computer has some important properties. Programming means to change the structure of the computer. A very important property. That's all we must do. The rest will be done by the system itself. Another point of view: everything is a control loop. This means solving differential equations. That's the job of an analog computer. So everything can simulate it by an analog computer. And further, impossible on digital stuff. An analog computer scales flat in inflection to the computing time. And, not worth the trouble, you cannot hack an analog computer. So far, part 1. Let us compute analog. We begin simple. 1 plus 2 equals 3. That's the hello world here. We have no keyboard. We can only enter numbers. You see an educational analog computer from 1965. For more, watch the following YouTube video. Here I show you the hello world for analog computers. This is a very old one. It's from 1965 and operates with tubes. The voltage is up to 100 volts, so it's a little bit dangerous. But let's look for it. The control unit is this part. Here is the input, the potentiometers. Here are the amplifiers, which we need to calculate. You can see that we use for the output this analog voltmeter and this digital voltmeter. They are showing the same, you can see it here. So let us look for a detail before we start. A little bit more here. We have here a summer. You see here the resistance input 1, input 2. Input 1 is coming from this potentiometer. Input 2 is coming here from this potentiometer here. Then we add it, and in order to have a positive signal, we invert the signal here with this simple inverter. Okay, let's go a little bit back. High voltage on. Nothing to see. What's that? Use this one. Here we can test what's going on. The hello is here. A little bit more, please. It's very difficult with this machine. 1 volt is a hello. The world is here. Wow. Très bien. 20 volts. Let us look at the analog voltmeter. That's very difficult. Okay. Not so fine. Back. Digital is okay. So, now let us look for the sum. The sum is at the output of this machine. Where is the output of this machine? This is here. As you can see here, we have minus 30 volts. And that invert that. That is this black wire here to the inverter. And now we have to go here. And you see 30 volts. Hello world. This is an analog computer. Heathkit, built in 1965. A wonderful machine. But a very basic machine. Here we handle the resistance. Later on we will see a machine which is a little bit more comfortable. So, go on. Okay, you have seen this video. But an analog computer can do really great things. Look at this ad from 1956. A rocket was really a dynamic problem. Today it's too a dynamic problem. Okay, part 3, the digital analog computer. The job is implement a program that simulates an analog computer with the possibility to run different analog programs on the simulated machine. A digital analog computer. Here a list of requirements and simplifications. No graphical user interface. Command line is okay. A simple usable interface for the analog program. Initial conditions, the inputs and the program. A graphical output. A solution to save the analog program and the results, also to export them. No dynamical variation of inputs, like a flight simulator for example. 10 analog computing units. Variable time steps dt to control the accuracy of the numerical integration. Variable number of integrations. Solve the mass spring damper system. Solve the simple predator prey systems. A short walkthrough. First we need a control for the simulated analog computer. Within the program, I called it ACSim, this is the outer loop. Starting this program means switching on the computer. Now the computer is ready to receive user input. Which analog program should be executed? What are the parameters? How long should be calculated, for example? Start the analog program for the entered time. Show the results. End the program. Switch off the analog computer. With run, the simulated analog computer must read in the desired program with the set values, then it performs and saves the calculations. Since dynamic processes are to be calculated, the flowchart must be run repeatedly through again, results at time t1, at time t1 plus dt, and so on. A middle loop controls the number of the runs. The actual calculation, the one-time step-by-step processing of the flow diagram for one point in time is done by an inner loop. The mathematical operations can be defined as functions which are called by this loop. The analog program itself is stored in a database by two tables, table initial conditions and table program. The results of the simulations are also stored in this database in a table with a job name. The results can then be output in tabular or graphical form. For this project, I have chosen the following technologies. Language, Python. Storage, SQLite database. Input-output analog programming. We can see it in a DB browser SQLite. For the graphical output, I use Matplotlib for Python. I work in Visual Studio Code on a Mac. And with a real-life analog computer, eSkeet EC1 we have seen, and an GTE 22, which is comparable to the Telefunken RRT series 700. A short look to the code. More you can find on GitHub. We have a main outer loop. We can change the database, the number of turns, the time scale. We can run the computer. We can plot the results and quit the program. In the middle loop, we control the turns, and in the inner loop, we do the execution. Important, the time scale is not connected to seconds or so. The differential equations define the time scale. The user can, for example, choose a year or a second as time step. Let's go. We enter the data. These are the potentiometers on an analog computer. In the program, we use a table, the table initial conditions. You can see it here on the right. Then we have to program the analog computer. What you see is not a server rack. You see the patch table, where we patch the combination of these units. For example, multiplication, division, square, whatever. We have here some units we can patch with these cables. Then we run the simulated machine. Important is the integration. I have chosen the Euler method, a first-order numerical procedure for solving ordinary differential equations. And if you repeat these small steps from today to tomorrow, we can go through the time and mostly solve the problem. The output. Here you see a picture from the terminal. The results, what we are doing here is we integrate over 1 after 10 time steps, or with a time 10 we have 10. We integrate a second time over this one and we get this one. This should be a parable, but as you can see here, we have an error. Look for the time steps. Here it's 0.5, excuse me, and here it's 0.01. That's fine, that's not so fine. Remember Euler. Okay, let's test it in the details with physics and a real-life GTE 2022. Sorry. Let's look for the mass spring damper system. This is a classic of physics and mathematics to solve a simple second-order differential equation. AC can simulate this. See the README for more. For testing here, we forget the damper and route the problem to this one here. Y, two-stroke, is equal to minus k, a constant multiplied with y. We draw the flow diagram. That's the first. We integrate y two-stroke, we have y stroke. We integrate y stroke, we have y. Then we have to multiply with a constant, k. This is this one here. And change the sign. We can do this also here. We multiply with minus this horrible number. And then this one is equal to y two-stroke. Two-stroke. Let us go to the demonstration. I show you a simple solution of a special differential equation. We look for a thing which is a little bit swinging, like a mass stretching a spring. What we need is an equation. It's this one, you can see it. The second derivation here is the same as the function itself multiplied with a constant k, but minus. This differential equation we solve now with this analog machine. Let us look for the equipment. First we have inputs. The inputs are here, these potentiometers. The program itself is this one here. If we program the machine, we change the structure of the machine. That's a very important thing. Do it with your notebook and forget your notebook. But now let us look further here. This is a control unit. The machine is running already, but not calculating. It's in a standby modus. We have here as output a digital voltmeter and a scope. You can see on the scope nothing is going on. So I start the machine first to see what's going on. You see nothing, but wait. What is that? That is the solution. I stop it. And what you see? Nothing. We start it again. And it's fun. It's very fun. So, now let us look for some details here. We have to go here, and here, and a little bit more there. What must we do? This part here is an integrator. This part here is an integrator. And this part here is an inverter. So we integrate the second derivation from here to here. Then we integrate the first derivation from here to here. Invert it. Then here is a potentiometer. We can choose the constant K. You see, there is something happened. And that's it. But one thing is very essential. We must stretch the spring before we start. This we do here in the analog machine with an initial condition. We can use this potentiometer. Here we have an initial condition of 1 volt about. And let us look. For the voltmeter, it's really running. It's about 1 volt in the maximum. So now we test it. Stop again. We set the initial condition from 1 to 2. This is here 2. It's about 2. Start the machine again. And let us look. We have here, from there to there, 2 volts. That's all. We have the solution. And as you know, there is a phase difference with the first derivation and the second derivation. So we can do this here, and this here, and then we can easily see the difference. A little bit more in the time scale. Looks like this. And now we change the plotting. And what is this? This is a circle. This is the x-axis, the first derivation. This is a function. And first derivation, function, phase difference 90 degrees, brings us a circle. A figure called Lissajous figure. This circle can be used to prove the accuracy of the machine, but it's not our job here. Let's go back. It's this one. That's the principle of an analog computer. You see, it's very easy. The only thing you have to do is to patch the program, but you must know the differential equation, and then the rest, a little bit of electronics, that's all. And now, to do more, buy an analog computer or simulate one. That's my part in the project. Okay, we create the database for this example. Look at the table above. We have two integrators and a constant multiplicator. Here in this table, the first integrator has the initial condition 0.5 and the constant multiplicator has this minus 39 and so on. When we run the program, we have this one. As you can see, it's similar to that we have seen on the GTE22. Let us look for some mathematics. In order to the accuracy, we choose a time period of 1. Time period here is set to 1, so we have this horrible number. And when we then look to the green curve, it should cross here the t-axis and not here. So here we have an error. In order to get the amount of this error, we look at the job table. This is this one. And at time t 1.0, we have this here. Minus 0.02. This is a little bit, but it's about 2%, and that's really an error. But the software is only a solution as a proof of concept, so we accept it here. Let's look for another example, or better, an application. Predators and prey. We begin here. A simple robber prey system was created by the sale of fur. We start here the number of snow hare and lynx skins purchased by the Hudson Bay Company from 1845 to 1935. This is a very horrible diagram, but we can see here are some interest differences, some phases. We must look further. The job was done by Lotka-Volterra. The Lotka-Volterra equations, also known as the predator-prey equations, are a pair of first-order nonlinear differential equations, frequently used to describe the dynamics of biological system in which two species interact, one is predator and the other is prey. The populations change through the time according to these pair of equations. We have for the hare this changing and for the lynx this changing, with some rates which determines the populations. And this will be solved on an analog computer. This is a flow diagram. The upper part here is the lynx population. The lower part here is a hair population. The multiplier here links these two parts. Here we have a very simple assumption. The number of luxes is proportional to the number of hairs, and inverse. The number of hairs is proportional to the number of luxes. Look back to the equations here, and then you see it here. You can factor out here the H and here the L. So the flow diagram gives us a deeper insight. Now we have to create a table. We have to integrate, we have to multiplicate, we have multiplication with a constant, we have adders here and here, that's this one, and then we can run the system and look for the result. This is a plot of the program. We can see the typical wave shape of a predator-prey system. Yes, I know there are only whole animals. The curves should be stepped, but for large populations, continuous curves are used. Not our problem here. The example shows that it is possible to solve systems of differential equations with an analog computer and the program. We do not need a special language for programming. So let us come to the end. Features of AC-SIM. With a simple program and a database is programming without a language possible. Feature 2. Classical analog computers can simulate it with digital equipment, but there are some disadvantages in the digital world. That's not our job here. Feature 3. The project is directly related to current research, for example, neuromorphic engineering, and therefore for artificial intelligence. Look at the README. You can do some homework. I do it not at the moment. This one here, SARS crisis. Compare the method of an analog computer to other methods of dynamical simulations, like system dynamics. For example, look at Berkeley Madonna, Ransom, Wolfram, MATLAB, LabVIEW, and so on. For application, look at En-ROADS, the climate crisis, the SARS crisis, but first, overall, stay healthy. For my first Scratch project, this one, to here, many thanks to David, Brian, Doug, and all the others from CS50. More informations, look at README, you find it on GitHub. This was created in France by Klaus Paschender, also known as Yukon-Ku. Feel free to contact me. This was Programming Without a Language, a project for Harvard CS50. This was Klaus Paschender from France.